Okay, let's start. Yeah, about time to start. Convective heat transfer, forced convection, is driven by the flow, and we had written this equation for nu times second derivative. This equation was written for a flat plate boundary layer. This is u of y and this is t of y. Okay, so let me now add to this the equation that we would solve for getting temperature. Yes, the class has started. You still want to shift more chairs. The equation for temperature, which is nothing but the energy equation, has a form like this. Cp. Let me write it as rho and Cp. Let me make it slightly different here also. I'm keeping rho explicitly in the equation, and converting the viscosity to dynamic viscosity. On the right hand side of the energy equation, we have conductivity times the second derivative in y. Okay? Yes. It is a differential form of the energy equation, yes, with certain modifications. So, the derivation I'm not going through. We will see, I'm showing the equation to, well, the form of the equation you can see that, have you heard of total derivative, material derivative? So, this is part of the material derivative. This is also part of material derivative. It also has time derivative. So, in certain way, this looks like the material derivative, which is, if I have to write this way, d dt, right? And on the right hand side, we have the conduction terms. So, material derivative is time derivative plus space because of flow. Because, yes, exactly, because of flow. So, this is the part which comes in addition for the flow. How is temperature being carried by u and how that changes in x? That gives you the net change in x, gives you the change at a given point. And how temperature varies in y and how that gets carried in by v, component of velocity. So, this is the flow component. And if it was unsteady, then you would add a time derivative and you make it a full material derivative and so on. So, there is a connection between what we have written earlier and what we have it now on the board. I am just not going into details to just get the main idea across. These, as I said, the area itself can be multiple lectures, multiple weeks of lectures. So, what I wanted to notice is the similarity between the two equations. They have exactly the same form, and of course, we have written it for steady, incompressible, flat plate. V infinity, T infinity. A flow over a flat plate, developing a boundary layer on the plate, a velocity boundary layer, also a thermal boundary layer, and the thermal boundary layer is responsible for the heat transfer that's happening from the plate to the flow, to the fluid. Okay, let's go back to the first equation and recall what we did last time. We worked with non-dimensional equations, non-dimensional variables. u star equal to u by v infinity, and so on. We defined it last time, all the variables were non-dimensionalized, which gave us an equation which was the same form, but with non-dimensional variables, and this we used to bring in the Reynolds number. And I am doing this to repeating this step to show how this similar procedure will be applied to the energy equation and what numbers come up from the energy equation. Okay. So, if we were to solve an equation like this, it is a partial differential equation first of all, compared to conduction, which we did solved for a very simple plate situation, which happens to be our turbine blade curved small section. Their temperature was only variable, and it was only variable of x or y, whichever one dimensional. We could solve it. This one, if you have to solve for u, you have to solve for v, and for heat transfer you have to solve for temperature, and all of them are functions of x and y. So, we have three unknowns u, v and t. Density, let us say, does not change, assuming incompressible, it is given. Viscosity, conductivity are all given properties of the fluid. We still have three unknowns and two equations. Yeah. Yeah. So, you can't solve it. You can, because there is one more equation. So, you nod it now this way. What is the third equation? Continuity equation. In fact, if you bring in, there is also a y momentum, but if you look into it, that does not give you anything more. But okay, so let's forget. So given that, all we are trying to say is it's a partial differential equation. We have not just one but three unknowns, and those are unknowns of x and y. So solving is pretty tough, very difficult. But then you have actually used solutions of these equations probably in some way or the other. A152, have you? In A152, let me write this down. You had something. You looked at flow around an airfoil, right? How is the flow around airfoil? We did that, and then we said it generates a lift and a drag and so on and so forth. And I'm sure you calculate drag and lift on an airfoil, which are essentially nothing but governed by these equations, but you never looked at the equations. Agreed? How did we compute the drag and lift on an airfoil? Yeah? Yes? Okay. We assumed what? Half rho v square? CL. The key thing is CL. And it's the same point we were making last time. It's a non-dimensional coefficients, non-dimensional form of the thing that you compute. You want to compute the lift, but you can't compute the lift directly. You have to first compute CL. And you get CL from? Yeah. Correct? Yeah? Potential. Did you do potential flow theory in this? No. Okay, we didn't do it. Right. You can actually get CL from that. You are absolutely right. But what did you do in AE152? Exactly. So you got to the back of the book, which has plot like this: CL versus alpha. This part we remember. CL versus alpha. And from here, given the conditions, we take CL, and then we apply it to our aircraft wing, if that's the problem. We compute rho, v and everything given at the altitude that is flying and get lift. That's precisely the point we were making in the last class, that this plot was not generated using aircraft wings. They were generated using model airfoils in a wind tunnel, smaller airfoils. But the connection between the wing and the full scale wing of an aircraft and the model that you're testing in the wind tunnel is the non-dimensional coefficient. So we said once we normalize it, CL is a function of, in fact we did CD last time, Reynolds number, and so is CL. So all the non-dimensional coefficients, which are force divided by dynamic head times an area. right. So, those are functions of REL, and I am saying that once again because soon we will define a non-dimensional number for heat transfer. We will figure out what are the parameters like Nusselt number, we determine that quantity and we will use those formulas. Use those formulas based on data like this, which people have put enormous amount of effort and time to do experiments and compile them for you in the form of charts like this or in the form of some formulas, some extended long complicated formulas. Yes, question.
Can we solve the continuity and the equation independently of the equation?
Of course you can. Yeah, assume T is constant, just for that. You never did that in your A152. Say again? The Blassius flat plate is exactly that, right? Temperature is not in the part of the story.
So can we just plug in that solution and solve the temperature?
You can possibly. You can. If you know U and V from that, you can solve for temperature. In fact, I think that's what they did. And I'm going to give you the answer. Yeah, it may look like a great, but people have figured it out and did exactly. So Blassius did the momentum part and somebody applied that to temperature. I don't know who, because Blassius was more famous because he's the first one to get any form of answer from these equations, right? So we remember his name, but I forget what is that. If he or somebody else did the temperature part. But the idea is that the same equations are far more complicated to solve, so we cannot solve them. We have to play some tricks, and the trick is happens to be in this case in terms of non-dimensionalization, get groups of parameters which form a non-dimensional group. Reynolds number being one of the easiest and the most common one for our this lecture. And we say once we take the drag, lift or any kind of force, any kind of quantity, non-dimensionalize it, and that will be a function of the non-dimensional quantities only, right. Now, just out of curiosity, this is a CL versus alpha plot, but here we are seeing CL is a function of Reynolds number.
So that is for a space.
Let's sorry, no problem. You have a good answer probably. Let me just see a bit on the other side. We never had alpha in this whole equation. Anybody from that side? No? Where did alpha come up? Yeah. It's for okay. Now let's a little bit of for those who are it's for the given geometry. Where does geometry appear in differential equation? For those mathematically oriented. Yeah, sure, but the same L can have different alpha. Alpha doesn't quite. You're getting there, but yes, at the back. I'm sure if you try, you'll get it. If you write a differential equation, we say we solve this equation and get the answer. If you can solve it, there are computer codes which can solve it. There are. Potential theory is a long time old thing. There are computer codes, CFD can solve it for you. But where did alpha come from? He said geometry, which seems to be right. But how does the geometry get into the differential equation, the mathematics of this? Conditions, some conditions, yeah, boundary conditions. It's just a simple thing. So this equation or any of these equations plus boundary conditions. So boundary conditions is where what brings in the geometry, which we didn't really say so much clearly. But if you have an airfoil, you match the shape of the wing that flies in the aircraft to what you test in the model and place the two in the same angle of attack. Fine. That is where the boundary conditions are coming in. Fine. Okay, no problem. So this is it. So we'll apply the same idea to heat transfer. Let's do it here. For non-dimensionalization, we look at the temperature profile, which I had just drawn here, something of this sort we have been using. This is Y, this is T. For time being, let's assume that we have a wall temperature and we have a T infinity. So we have the two ends, if we call them boundary conditions, that let that be. So we define T star as T minus T infinity, I think, divided by T wall minus T infinity. For velocity, we didn't do all that minus and all that. We just said U by V infinity. Here there's a little bit more. Because heat transfer is governed by temperature differences, not temperature alone. If T wall and T infinity were same, the problem was trivial. We don't need a solution for it. the solution is given. So, with this, if you work it out, you would get rho Cp, let us make it rho infinity, rho is constant, one more thing, let us write that, u star, u is normalized the same way, so I am going to put V infinity here, u star, this term, plus the y term, which I am going to make it short, which you can fill in if you need to. And there will be 1 over L because of the derivative with respect to x star in the denominator. On the right hand side, we would get K. Oh, I missed out something. Okay, let's write this down anyways. Agreed? No? Okay? We're still busy writing. We're going to write it and then we'll see. Let me do a few manipulations in the meantime because I know the answer that I want to get to. I would say that, of course, I divide through, I take the ratio of these two terms, the coefficients on the two sides. I'm going to write this as rho K over rho Cp, and I'm going to write it as V infinity times L, trying to get to something which we know or we with. Let's call it rho infinity, and somebody tell me if this equation is correct or not. And K over rho Cp is a new parameter called thermal diffusivity, all right. So the equation is correct, I assume, right? Nobody wants to commit. Okay, you guys figure it out because we have to still finish the material for today. I think the equation is correct. The only thing that is missing is I have not put in this factor on the two sides. When you replace temperature with T star, you have to multiply with Tw minus T infinity. And this part, so you can work this out. This would be T wall minus T infinity times T star plus T infinity. But we're taking derivatives, so the last plus T infinity does not matter. But that additional factor would come, it will come on both sides, it will cancel out. Okay, so this is called thermal diffusivity, and there is a, so I'm going to replace this by alpha, and I'm going to get kinematic viscosity on top because that is something we are familiar with. We know it's a Reynolds number, and kinematic viscosity on the bottom. Agreed? This one is 1 over Reynolds number, and the other quantity, this group, is called Prandtl number. PR is kinematic viscosity divided by thermal diffusivity. Both happen to have the same dimensions. So that ratio gives us a non-dimensional number, Prandtl number. So what you get is a ratio like this. So, essentially your equation you are solving is U star del T star plus the V term equal to 1 over Reynolds number Prandtl number times the temperature derivative, but in all in non-dimensional form. And just the way we had argued that once we have the non-dimensional equation, the solution will depend on those non-dimensional terms like groups, like Reynolds number, and any quantity we compute, whether it's a friction at the wall, shear stress or the drag, whatever it is we compute, they depend only on this in the non-dimensional form. So, for heat transfer as well, the two numbers that matter are these two. Reynolds number depends on, well, we should write this down here, let us say once, RE L equal to rho infinity V infinity L over viscosity. So, it depends on density and viscosity of the fluid, it depends on the flow velocity, and it depends on the size of the body of the plate in this case. Prandtl number is a ratio of kinematic viscosity and thermal diffusivity. You can write it as mu over rho. How do we get this? Mu over alpha is rho Cp times conductivity, right? So, replace alpha by rho conductivity. No, I made a mistake. Mu Cp and rho gets cancelled. Okay. Mu Cp, I think this is true. Let us try this. I think this is what it should be. Mu Cp over K, rho would get cancelled. Cp is property of the fluid of air, we know what the value is. Conductivity is also a property and so is viscosity. So, this guy Prandtl number does not depend on the flow, does not depend on the geometry like Reynolds number or size of the body, it depends only on the fluid properties. It happens to be 0.72 or 71 for air. Okay. So, if we get a non-dimensional form of heat transfer, then it will depend on only these two values, and let us do that. Heat transfer, at least in the case of a flat plate boundary layer, what we are interested is the wall. Heat transfer at the wall is minus K dt over dy at y equal to 0, fine. Make that into non-dimensional quantities, minus K T wall minus T infinity times this. Yeah, L, thank you. Okay, and then there is one more thing that is brought in, and that is called a convection coefficient. This is written as Q as H times T infinity minus T wall or T wall minus infinity. I made a mistake? 1 second. T wall minus T infinity. Yeah, question? What was delta? This one? Well, we have actually, okay, let me write that down also. We had a slight thing in the last time, y star was y over, we wrote delta, but in fact it can be non-dimensionalized by L as well. In fact, the equation REL will come if you non-dimensionalize it with L. Otherwise, we will get an additional factor of delta over L hanging around, so we have to kind of take care of it separately. So, what we are doing is u star equal to u over v infinity, v star same way v over v infinity, x star x over v L, y star y over L, and temperature T star is given here on the top, we defined earlier, just to make it everything complete. There's not, the problem doesn't change so much if you non-dimensionalize y with delta. You just have to keep track of that, one additional thing. Yeah, we brought in a delta there as well. So I think they'll all take care of it. You're right, absolutely right. So let's do this one. This is actually kind of fairly consistent way of doing this. Okay, so here I'm just a little bit doubtful about the TW, T infinity minus TW. I probably made a mistake here. I think it is the other way around. The non-dimensionalized form of T, where the T star is defined as T minus TW divided by T infinity minus TW. Much of the algebra will remain the same. It's just a things will cancel out, but it's the other way around. So I think this would be T in this also would be different, T infinity minus TW. Yeah, thanks. Okay. So this one is called the convection coefficient. And if you plug these things in, what you would get is H equal to K over L right, you can see through. And we are doing this to get slight modification HL over K equal to this. Remember that we are looking for non-dimensional groups of numbers, and that happens to be our next non-dimensional number, which is called Nusselt number. So let's step back and see what we did. If for momentum, when we write momentum equation, what we would like to get out of it is friction, the wall friction, the shear stress. So if you solve for momentum equation, you would get the velocity gradient, the velocity is a function of x and y, you take a derivative, you get the shear stress. That has a dimension. We convert that into a non-dimensional number called CF, skin friction coefficient, right? And skin friction coefficient is a function of Reynolds number. Skin friction coefficient is a function of Re for time being, let's say. Here, when we solve for the energy equation, get temperature as a function of x and y, we would like to get the heat transfer, Q. But we want a non-dimensional form of heat transfer. Nusselt number happens to be that. It's not that easy to see, but Nusselt number is a non-dimensional number which tells you what's the value of H is. For a given length of the plate and for a given property of the plate, of the fluid, conductivity of the fluid. Once we get H, heat transfer will come straight away out of it. So, H is nothing but a simplified version of heat transfer. So, Nusselt number is now equivalent to skin friction coefficient in heat in momentum. And if we put the things together, what we will find is Nusselt number is a function of Reynolds number and Prandtl number, because the equation has two. The equation as we wrote it has two of these non-dimensional numbers. This is the equation in a normalized non-dimensional form, which has Reynolds number and Prandtl number. Of course, if you are considered only with air, Prandtl number will remain constant as far as majority of our applications go. And if you get the value of Reynolds number, you can calculate Nusselt number. And there people have done this and given us this form of this expression, where I am calling it a general function, but we have actual equations and the way we can compute it. So let's look at one of those. The simplest one happens to be laminar boundary layer on flat plate. We have been dealing with flat plates for the entire this convection problem. Now we are seeing the flow, in addition to flow on the being on the flat plate, it's also laminar, and we know when it is laminar, when it's turbulent. But if it is laminar, it's the simplest situation. Blasius solutions are available, which are called Blasius profiles. So he took the equations, differential equations, and solved them numerically without a calculator or a computer at that time. But what we got, he got a couple of useful results, which I am going to write here. He defined Reynolds number in terms of the distance x from the tip of the plate, the same definition like REL, but L replaced by x. And he said Cf equal to 0.664 over square root of REL. So, REx is a Reynolds number defined based on x being the distance from the tip of the plate to wherever the location we are interested in. So, Cf now is a function of x. Cf is changing from point to point. The shear stress would change from point to point on the plate as a function of x. And the Nusselt number also, the local Nusselt number defined as Hx over k is given as 0.332 square root of Rex and times Prandtl number to the power of 1/3. There is one more Nusselt number where a slight modification that is usually more useful is an average Nusselt number based on the length of the plate, and we put a bar on top, is defined in terms of an average coefficient of convection HL by K. This H bar is an integrated version of H. So, H is a convection coefficient, how the heat transfer is happening at every point, and that varies along the plate. It depends on how thick the boundary layer is, and yeah, that's probably that's the only factor in this case. and you integrate the whole thing over x and say, can I compute an average value of convection coefficient? That is h bar. Unless the length of the plate is L. So h bar gives us Nu L bar is 0.664 REL square root times Prandtl number to the power of 1/3. Weird, right? There are more weird things coming up. This also still happens to be the simplest one. And this also happens to be something that actually can be solved from the governing equation, the way we lined up the momentum equation and the temperature equation. Most other situations you cannot really solve it. Yes?
Can we, there was a Barbarian approximation by the velocity profile,
Okay.
which was parabolic. And we have a similar something.
I'm sure, yeah, people must have done it, you take a velocity profile which is some form of approximation and work it out.
So if we have that kind of a profile, things will be easier than this and more connected.
So if you have a approximate profile which is parabolic, we know that the boundary layer is not parabolic, but you're saying if you assume approximately, you can probably actually work it out easily. Here I'm not showing the steps because a part of the process is actually numerical. You cannot solve it so easily in this, but it can still be solved, and it is the final answer. We're not making any approximation beyond a point.
How well would a parabolic approximation?
That is something we have to look it up. I don't know. But in fact, what happens is many other situations you cannot solve it numerically like this, or neither can you solve it even with assumptions. So there you have to rely on experimental data, and one example is if the flow was turbulent on the same flat plate, which we know after a point it will become turbulent. You would have a formula which is a little more weird, which says Nu local as a function of x is 0.0296 Rex to the power of 4 by 5 Prandtl number to the power 1/3. And you cannot derive this whichever way we want. We have to rely on experimental data. People have done lots and lots of experiments, plotted data for Nusselt number as a function of x and the Rex, and tried to fit some curves through it. So these are all empirically obtained values. Empirically obtained from experimental data. So much of the useful results that we can actually work with to estimate heat transfer essentially depends on experimental data finding. Yes, question? Yeah. Correct. So there are certain approximations that you apply to get somewhere, but then you try to fit through the data to get some of these constants to get the final answer. Yeah, you had a question? No, you don't have to remember any of this. If required, we'll give you the values, give you the formula. Okay, let me give you one more. Which may come out handy is for a flow through a pipe. turbulent flow through a pipe, this would need some effort to write, but that is the one. It's defined in terms of diameter of the pipe, because that's the length that we have. We don't, the pipe may be infinitely long, but the diameter is a more relevant parameter, and that happens to be f by 8 Re diameter, based on diameter, minus 1000 times Prandtl number divided by 1 plus 12.7 times f over 8 to the power of half Prandtl number to the power of 2/3 minus 1. So, this is the easier way than solving the full equations, if you want to take it, where f is still not the end, more to it, 0.79 ln log of Red minus 1.64 to the power of minus 2. And Re, Reynolds number based on diameter, is probably, you can guess, a flat plate, a pipe still have the simplest geometries, for which we have these expressions. All are experimental, except for the laminar boundary layer. Much of these are experimental data, based on experimental data. We can find some form of, like, if you make some approximations, you may be able to get some of these powers out of the analysis, some of the derivations, but the actual numbers that you get are definitely from experiment. So, you kind of have, if you do a detailed derivation of these from these equations, you may get some idea of what the curve should look like, what the formula should look like, what power of those formula of these terms. But then you take those and then fit to the experimental data to get the actual function in terms of all these numbers, f by 8,000, enough number of numbers which are based on fitting to the experimental data. But now imagine the problem that we had set up in the last class. We have a turbine blade through which you are passing a coolant, and if we want to look at a problem like that to see if how to apply this, we can't solve the full equations in any way for such a problem without using fairly complex computer codes. But we don't have computer codes when we are sitting in this class or solving the tutorial or exam problems, but here it is, a turbine blade like this, and we said this section is part of a long blade, much magnified view, and through the blade we have certain ducts cut out inside the blade that we are passing fluid, coolant. So then, at least to make an estimate of the heat transfer, one can go about saying that the surface is some form of a flat plate, not so different from a flat plate. Maybe we can apply those formulas which we have, the top and bottom, and inside those channels where we are passing the coolant, we can apply maybe the pipe flow formula, maybe, because we don't have anything better right now. But if you do, then let's come back to the way we had set up the problem for conduction one more time, saying here is hot combustion product, here is coolant. Of course, direction of flow may be different on the two sides, but let's just to put the thing together. And we want to know what the temperature distribution is inside the material of the plate, and we had initially set up T hot and T cold as the boundary conditions. Now you can, if you go back and see really what's happening, there's a flow of coolant and there's a flow of hot gas. There are two boundary layers on two sides. And the boundary layer, we have to find out what is the rate of heat transfer because of convection on the coolant side and the hot combustion product side. And those values of heat transfer would essentially come from these quantities. So, knowing the flow parameter for the coolant, let's say, the property of the coolant for which conductivity, viscosity will give us a Prandtl number for the coolant. We can compute the Reynolds number of the flow if you take it as a pipe, knowing that having an estimate of the size of the pipe inside the duct that through which the coolant is flowing. Having an estimate of velocity and density, we can compute the Reynolds number, apply this to get Nusselt number. From Nusselt number, you go back to find the convective heat transfer coefficient, and then we get Q. And that is the heat transfer that's happening at this point. So, TC may not be a good estimate. We say Q coolant is the heat transfer. That is really what's happening. The coolant temperature is Tc, and the hot exhaust has temperature Th. That may not be the temperature at the wall. If there is a boundary layer, what we say the flow outside the boundary layer is we know T infinity, that is Th or Tc in this case. Inside the boundary layer, the things change. So, in fact, we made a picture of this I think last time by saying that there will be a gradient in temperature in the coolant side and there will be a gradient in temperature on the hot gas side, and this would be QX. So, that any realistic problem like this would have convection, conduction and convection, and we have to couple all of this together to get a reasonable estimate of things, even with all the assumptions of this is being a flat plate and this being a circular pipe. And of course, you can change, if you can find data for a square pipe, fine, go ahead and let's pull that data out and use it in the form. For that matter, if you have data for not a flat plate, but let's say a cylinder facing a flow, the nose part might actually resemble more like a cylinder than a flat plate. So, we have to be more imaginative, more creative to find out good data, if there is data available for any of this. Yes. Sure, you can do it if you have it was in your hands, but let somebody has already done it for you, because this you may want to maximize the area as well. I don't know. There may be other constraint that determines whether the pipe should be cylindrical or square. Maybe structural conditions may be required. This looks like, I don't know if you have had a structure course. This looks like the construction of an airfoil when you have these I-beams inside. So, there are many other constraints. What I am saying is somebody has given this to you and now you are asked to compute the heat transfer. You have to use what you have. And in fact, this point happens to be the most crucial part of the heat transfer problem. That's because it's a stagnation point. And stagnation point, heat transfer, pressure is highest at stagnation point. Same way heat transfer is highest at the stagnation point. And more than that, stagnation point depends on, if you remember this, T stagnation, if you call it this, T naught over T equal to 1 plus gamma minus 1 by 2 m square. So, T is what's coming up far away, T infinity, let's say, T infinity and m infinity. So, at the stagnation point, you would go up by a factor of whatever that is on the right hand side. And now tell me if the blade was not stationary but spinning, would that increase or decrease the stagnation temperature? Increase. It's a relative Mach number. So the temperature of a fluid, static temperature of a fluid does not depend on whether the fluid is moving or at rest, but total temperature does depend on that because your kinetic energy gets added to it. It's a frame dependent quantity. So the turbine blades, they're facing the hot combustion products. The tip of the blades are facing the stagnation temperature. On top of it, the blades are moving so fast, especially if you go far away from the hub. They probably are moving at almost a sonic speed. So that much factor that will be added to it. If it is close to 1, this will be, I think, 0.2. So it's a 20% more heating is happening on the turbine blade tips. And that's why we say that the material requirement of this turbine blades and the tip are the most critical one for the entire engine design. And those are temperatures that decide the highest peak temperature of our Carnot cycle, in terms of Carnot cycle or any cycle. So here is everything comes together. The last part I said is that if there's heat transfer happening on a turbine blade, this happens to a section of a turbine blade, the front part is what is facing the maximum amount of hot gases. And the way to quantify it is that there's a stagnation point which will have a temperature higher than static temperature. So T infinity is the static temperature coming in from the combustion chamber, but this guy is facing higher than that by this factor. And this factor could be high depending on M infinity. M infinity could be up to Mach 1 or more. You want an RPM of the turbine so that the tips are close to sonic speed. Beyond that, the losses are too much, so you keep a restriction on that. Okay? We're just in time to end the class.